My name is Kyra Campbell, and I'm a senior lecturer at the University of Sheffield and part of the UKCCSRC. Some of you may remember that a while back, I hosted a webinar that looked at crossing over the challenges of decarbonization of industry. And we talked a lot about transforming foundation industries and how those link with the challenges we have in decarbonization. Well, so this is an outgrowth of that discussion, which was really successful and really opened our eyes in terms of understanding each other's points of view. And so this is going to focus on steel manufacturing and how we decarbonize the steel industry. And we're very lucky that this particular webinar is a partnership with Sustain. And I'm going to introduce Becky Waldram, who's here from Sustain, to co-chair this webinar with me. And we look forward to learning a significant amount about all the challenges around decarbonization and sustainability of steel. So, Becky?
Thanks, Kyra. For those who don't know me, I'm Becky Waldram. I'm the Impact and Engagement Manager for the Sustain Hub. Sustain stands for Strategic University Steel Technology and Innovation Network, and we're a 7-year future manufacturing hub funded by UKCCSRC with 2 years remaining currently on this project. We're led by Swansea University, where I'm based, and we've got core spokes at the universities of Warwick and Sheffield, and several smaller spokes across the UK through our feasibility studies and our early career researcher projects that we fund. We work a lot with the steel industry across the UK to address the challenges that they're facing in decarbonisation. Our main research areas focus on carbon neutral iron and steel making and smart steel processing, encompassing areas such as emissions management, reducing waste, looking at data-driven applications, energy efficiency, and sustainable metallurgy mostly. Our projects are all collaborative with industry and driven by that industrial need, bringing together those industry and academic specialisms we need to move towards net zero. So that was all I had to say about Sustain. Back to you, Kyra.
Thanks, Becky. That was really great to hear a bit about the overarching goals and the strategies associated with Sustain. So UKCCSRC, as it says in the title, is all about decarbonization and about the challenges associated with the process of CO2 capture, transport, utilization, and storage. And so today we'll be looking at the relationship between those challenges and the steel manufacturing industry. We've got a fantastic group of speakers today who will be talking from different perspectives on this topic. We've got Heath-Whyte from Liberty Steel Group. Then that will be followed by a presentation from Enrico Andreoli at Swansea. And the third speakers will come as a duo, Haroun Mahgerefteh from the University College London and Paul Cobden from Swerin. And you'll learn a little bit more about what that is as they get into the discussion. So with that, it's my great pleasure to introduce Heath-Whyte from Liberty Steel, who will be kicking us off with the first presentation.
So my name is Heath-Whyte. I'm Head of Environment and Sustainability for Liberty Steel UK. The picture there is of our Waldram steelmaking plant. We operate an electric arc furnace steelmaking plant in Waldram. This is the future of steelmaking in the UK. We've seen recent announcements. Obviously, the traditional blast furnace and Boss route in the UK will give way to electric arc furnace steelmaking, and Liberty Steel Group is the same as well. Our continental Europe plants and Australian plants will move to EAF steelmaking. The advantage of electric arc furnaces is that they are lower CO2 emitting processes. However, they don't emit no CO2. They obviously have quite a lot of carbon involved in the steelmaking process and also downstream processing of steel as well. So for Liberty Steel UK, our baseline year was 2019. And you can see there the sort of split of our baseline CO2 emissions. So this is for steel making, but also our downstream processing in hot rolling mills. So 51% of our emissions were from methane, natural gas, and some coke oven gas. And then 37% electricity, so a scope 2 emission. And then 10% is the sort of steel making part of that, so the addition of carbon and alloys. But for the direct CO2 emissions, the two major ones are carbon additions at steel making and the natural gas used within the processes. So the sources of CO2 in an electric arc furnace are obviously electricity, which is supplied by the national grid. That's an indirect emission. But for our direct emissions, we've got natural gas or LNG, or so oxy-fuel burners, ladle preheating, tundish and shroud preheating, and the cut to length in the bloom and billet. And then we have some actual carbon additions, so the electrodes that are used to provide transfer the electricity for the melting. We make carbon additions of coke, coal, injection carbon and carbon wire, and also within the alloys that we use, ferrochromes, ferromanganese, all of those alloys have carbon within them as well. So within the mass balance of the steel making, we retain some of the carbon in the steel, but we also emit the CO2 from the process. And then as we process steel further downstream in our rolling mills, we reheat the steel, and we heat that up to 1300 degrees centigrade. And we use reheating furnaces, soaking pits, walking beam furnaces, walking hearth furnaces. We do heat treatment of steel. We cut steel, and we use gas oil as a backup sometimes, although not so much anymore. So we have quite a large usage of natural gas, particularly for reheating steel. And that's not generally understood. People think it's all in the steel making, but actually the downstream processing has a considerable amount of CO2 emissions. So as a company, as a group, Liberty Steel Group have a climate neutral by 2030 ambition and strategy. And this is an illustrative approach to how we are approaching that. So first of all, we'll tackle efficiency of process. So we make sure that all of our processes are efficient in the use of energy and the fuels that they use. We'll fuel switch, so from coke oven gas to natural gas, and that's happened. And then if there's going to be a new grid or grid mix, then we'll switch to that. But we also look at where we're going to get hydrogen from as well. So our ultimate decarbonisation is to use hydrogen for our reheating and for various processes that we already mentioned. And that will replace the methane. So that's one part of it. We also are doing things like using biomass or biocoke to replace coal and anthracite. So this is where the sources of, well, it's where CO2 comes from, or was emitted from in the process. So we have different sources of carbon, and these are all from our UKCCS registry. So we calculate every year our tons of CO2, and those are verified, and we report those through the emissions trading scheme. So we've got carbon additions, coke and coal, so M1 and M7, natural gas, propane, gas oil, electrodes, alloy additions, primary alloys, and a small amount of acetylene. And you can see from all processes there that natural gas is the biggest, and coal is probably the second largest, and then for steel making similarly. So the key for us is to replace that methane, that natural gas, and that's what I'm talking about today. So the way we're going to do that is, well, primarily through the use of hydrogen, but we will also electrify some processes. This slide shows the East Coast Hydrogen Network. So this is a project, and Cadence, one of the partners in this project, and we are one of the stakeholders. So you might be able to see from the diagram there that we are in between Waldram, Doncaster, and Sheffield. So we are expecting to be on any hydrogen pipeline between, well, probably in the early 2030s, 2031, 2032. So we would expect to see pipeline hydrogen in that sort of time scale. And that hydrogen, as it stands at the moment, will be produced on the East Coast, either from methane steam reformation or through electrolyzers through wind power. But this, the diagram shows actually where the energy is coming from, so from wind, but also where possibly any carbon storage could be done, or usage of that carbon to make other things. So that's what we believe our strategy is going to be at the moment. This is as far as we can see. And we need the actual, because the amount of methane we use, we really need it to be from a pipeline. We could do it on site, but that could be a big issue for us. It's not our core business to make hydrogen. Our core business is to make steel, and therefore we prefer to get our hydrogen through a pipeline. So we expect that CCUS will be used in those processes that produce the hydrogen and then provide it to us. However, we've also done some research through the SUSTAIN project. So Professor Peter Swerin and George Dowson have got this rig. I'm not going to go through all the writing, but it's a test rig which is in a trailer, and that would been hooked up to our Brinsworth strip mill hot mill furnace. So we did a trial there, an industrial trial, just to prove this unit. It was the first trial of the unit, and we did this last year. So we were successful in taking the flue gases from the stack and passing them through the process. That provided quite a lot of learning opportunities for George and Peter in terms of how their rig operated and some of the issues they might have. We did find that the actual CO2 content was quite low in that stack. That's possibly due to air ingress between the stack and the furnace, but it was, only about maximum 2% CO2. However, they managed to capture that and also managed to concentrate that CO2 up to about 8%. So that was a successful trial of their process. This sort of enables them to then develop the process further, and the test rig we see there will go on to other steel sites in the UK and try other sources of emission, so other sources of CO2 to capture. We believe currently that it's probably not viable to capture CO2 from reheat furnaces using methane, but that does depend very much on the costs of the process and also the costs of hydrogen. So at the moment, what we're doing is ensuring that we understand both hydrogen to our sites, but possibly the use of CCUS on our sites as well. That's it for me. Thank you very much. Any questions, I'll answer them later.
Brilliant. Thank you very much, Ed, for that introduction to the steelmaking process and sort of the main areas where CO2 emissions are produced and some of the plans for the future. Just a quick reminder that if you've got any questions, please do put them in the chat and we will get to them all in the Q&A section later on. Next, I'd like to introduce Professor Enrico Andreoli from Swansea University.
Excellent. Thank you very much. Hello, everyone. It's a pleasure to be here today. As Becky mentioned, I'm Enrico Andreoli at Swansea University, and I'm currently heading the Department of Chemical Engineering. I'm also working with Sustain directly, involved as a co-lead of one of the tasks. And in today's presentation, what I want to do is to cover the work we are doing and where we are heading. And since this is co-hosted by the UKCCSRC, I thought it was an opportunity in the second part of my presentation to cover a project that we completed with their funding about scaling up the production of a specific carbon capture material, metal organic frameworks, as you will see in a moment. So what I'm going to do next is to go immediately, apologies, I'm taking my laser pointer, to the first slide about Sustain. So this is the team involved in emission management and utilization within Sustain. And you have seen already Professor Swerin in his presentation just now. With Peter and I, we are co-leading this specific task and involved in doing research. There are two PDRAs, Dr. George Dawson and Dr. Craig Armstrong. With our team, we are addressing carbon neutral iron and steel making with a particular focus in phase 2 of Sustain, which is converting carbon dioxide into products. So the focus of our work now is rather on taking carbon dioxide captured from steel making and converting it into value-added products. This in the center is the cover of the latest annual review of Sustain. You can scan the QR code. The reason why I put it here, Sustain has a large body of research all devoted to iron and steel making decarbonization. And if you want to learn much more than what I'm going to show you in the next 15-20 minutes, please go ahead and check the annual review. Here are the three partners, Swansea University leading, and the University of Sheffield, the University of Warwick, being working in the project with Sustain. So, introduction to the project. Now, this is quite a busy slide, so forgive me, but the message is very simple. The message is the following. We are approaching steel making from a point of view where we want to remove carbon from the equation as much as is possible. And you can see different approaches listed on the left-hand side of this table. And the most carbon intensive is the largest used globally today, blast furnace, basic oxygen furnace. And we know that steel making roughly contributes to 5% of the overall CO2 emission globally. And the reason being is for 1 ton of steel produced, about 2.5 tons of CO2 are emitted. So you can very quickly do calculations with the global crude steel production and see how many millions of tons of CO2 are emitted. There are different solutions being considered to decarbonize steel making. One, we just heard about electric arc furnace from head, would cut the reduction, the emissions to 0.3 tons of CO2 per ton of steel. But the point I want to make here is that even if we were to switch today entirely all global steel production to electric arc furnace, we would be still having quite a large emission of CO2. So 600 million tons a year of CO2 would be emitted. So in view of this, one approach is to look at this CO2 as a resource. Using it as a material, a feedstock of carbon from which to make useful products. And that's the approach we are taking within Sustain in our specific team. And the idea is that this product can become valuable, competitive in the future in terms of value to how they are made to date, and in this way create value to support capture and sequestration. And also create an economy centered, so a circular economy where all the carbon material we depend upon, including fuel and chemicals, are made from carbon dioxide. So with this in mind, within Sustain, we are working on 2 strains focused on making synthetic fuels from carbon dioxide, from steel making processes, and also sustainable chemicals from the same gases. So we want to take this carbon dioxide and generate either fuels thermochemically or chemicals electrochemically. So the 2 are 2 complementary approaches where CO2 is upgraded into a valuable product. The idea is to generate fuels for hard to decarbonize transportation, like aviation, and chemicals that are produced on a very large scale, like commodity chemicals. One indicated here is ethylene, for example, made in hundreds of millions of tons per year. So now I don't want to bother you or actually make it too complicated, but I want to give you a bit of a flavor of the work we are doing in terms of converting CO2, okay, in Swansea. So in Swansea, we focus on electrochemical conversion. And what we do in a nutshell, obviously oversimplified, we take CO2 with water. This is a proton coming from water, and electrons, so electricity. And we combine all of this together using an electrolyzer to convert CO2 in a series of products. One, for example, is this ethylene. And ethylene is building blocks of polyethylene, for example, so produced, as I mentioned before, in very large scale. There are advantages in using electrochemical approaches. One for all is that we don't need high temperature and pressures. There are others, but there are also disadvantages. One of these, for example, is that typically these processes are not too fast, so the productivity is not that high and not very stable. So we are approaching this problem, again, to take CO2 from steel making and generate products from it. So our approach is the following. Now, you might see a title here. This is called chloralkali technology. This doesn't have anything to do with CO2 conversion, but the reason why I put this title and this slide is that we want to learn from the largest electrochemical industry in the world, which is called chloralkali industry, to see how they do electrochemistry on a such large scale and translate their approach to one for CO2 conversion. Obviously, we have plenty of CO2 to deal with, more than we actually use. That's why we need also storage. And if we need to do electrochemistry with it, we want to learn from who does already electrochemistry on such a large scale. And this is the chloralkali industry. On the right-hand side here, you see operators setting up an electrolyzer. Actually, it's a stack. This is an industrial stack. In this picture, you can see how it looks like. There are several layers. So here inside here, there are all the components of the electrolyzer. But one I want to put attention on is this cloth that is being put on one of the sides of the electrolyzer, and is actually the part that is most important in the operation of this type of technology. It's called the percolator. The percolator allows for electrochemical processes to operate on a very large size. So we are talking about square meters electrodes where the conversion happens. And that's the direction we need to take also with CO2 electrolysis. We need electrolyzers of this size, very, very big electrolyzers. That's something that Currently, the academic community is probably considered, but we are at very early stages, and we want to take it forward to help scaling up CO2 electrolysis. The way we do it is to using something that we call gas diffusion electrodes. So these are electrodes that separate CO2 from the water that need to react together to make the products. So the CO2 permeates through this membrane in gray. The membrane has a catalyst on the right-hand side, and the process happens at this catalyst surface, and the products are made. Obviously, I'm oversimplifying everything. This hopefully that you can still following me as I explain how this works. Now, if we do this on very tall electrolyzers, the water on this side creates a pressure due to its own weight and density, and the pressure differentials that we create across this membrane creates very big issues from an operational point of view, because the pressure is higher on the top than in the bottom, and this makes the process unworkable. The use of that cloth I told you before is actually the solution to this problem, to equalize the pressure and to be able to do electrolysis on a very large size, okay? Something that is not being tackled at the moment. And that's instead something we are working on with Craig, I mentioned before. And we are working on testing this approach using gravity-fed electrolyzers that are tall enough to analyze the problem of electrolyte differential pressure. And this rendering shows a system that we have actually developed at the moment. So it's already in the lab. We are operating it as we speak. And shortly, we are testing the technology that is used in the largest electrochemical industry in the lab in order to be translating it for the steel making industry. On the left-hand side, you see a smaller version of one of these electrolyzers using what is called the falling film electrolyzer approach. And this is to give you a flavor of what are the different components present in the electrolyzer and how the technology is developed in the lab. So with this, I covered the first part of the presentation, where I wanted to give you a flavor of what we are doing in Sustain to address the electrochemical conversion of CO2 to create value from CO2 for steel makers. In the second part, quickly, I want to cover a project that we did with the UKCCSRC on scaling up a specific carbon capture material. You can see the name here. I don't want really to bother you with all the details about the material. You are very welcome to contact me later if you are interested. But what we did was to take this specific carbon capture material and scaling it up in Swansea University with the following collaborators. So as in Swansea with ESRI, the Energy Safety Research Institute, where I work, and Dr. Stephen Sheeran to do all the experimental work, and Associate Professor Marco Taddei in University of Pisa, who developed this MOF with his collaborator in Perugia, and was a Marie Curie Fellow with us in Swansea, and in Material, a Cambridge-based technology company specialized in MOFs, especially monolithic MOFs, who collaborated with us. So what we did, again, very quickly, was to produce this MOF, is this yellow powder here. So it's not really very complicated. It's a powder. This powder can capture CO2. Obviously, is more complex than that. There are many factors to consider, but I try to keep it simple. The powder can also be converted into, shaped into pellets, and it can be made very, very easily in water using relatively cheap chemicals. So we proved in the laboratory that the what in engineering terms we call space-time yield could be at a particular value that was of interest for industrial scale-up of production of this material. So why this material in particular? This material, by the way, I have another slide here. This can be shaped also in very regular form. Shaping is very important for an applied point of view for carbon capture materials. And this was done with the master student visiting Haroun from IQS Barcelona. So the material can be made, can be shaped in the form that can be used for carbon capture. And even more, and now I have a slide coming of work that we haven't done in Swansea directly, and is instead work from Marco Taddei in collaboration with Imperial College London, Professor Petit, and first author, Dr. David Danacci. I decided to put this slide because this work based on modeling shows how the MOF that we developed, we scale up, sorry, when we look at the utilization of this MOF in a particular setup, which is called pressure swing absorption, so where we capture CO2 using changes of pressure. So the CO2 is absorbed at high pressure and desorbed at low pressure to be separated and obtained with a certain purity and recovery. The black curve in these two plots shows that in terms of purity and recovery, this particular MOF is performing better than other MOFs or commercial standards like zeolite 13X and activated carbons, for example, compared to other materials. So something to say, if you are interested, please go and check this particular paper, because you will see there are many considerations to take into account. But the message I want to give is that this on the right-hand side, with the concentration of 25% of CO2, is considered as a gas mixture, a simulated gas mixture of value for steel making decarbonization, because in blast furnace, for example, CO2 is roughly 20%. These simulations, if I'm correct, modeling are based on balance of nitrogens. That to be clear, if it's not really gas from steel making. So the material has very promising performance and can be made on a large scale. And we are looking into options to continue working on this in order to translate it in something impactful that is being funded by the UKCCSRC. And we are very, very grateful for this. Since I talked about PSA, I think I still have a couple of minutes. I want to close this presentation with some work that we have done on developing pressure swing absorption demonstrator within another project that is separate from Sustain and UKCCSRC. However, very relevant, I think, for the audience today for industrial decarbonization. So the project was Reduce Industrial Carbon Emissions, funded by the Welsh European Funding Office and the Welsh Government, with Swansea University and the University of South Wales as partners, and led by Professor Andrew Barron as PI. And I was leading one of the work packages, where we developed this PSA unit. The unit has been deployed at Rockwell here in Bridgend, not far from Swansea. So now this is not a steel maker. They make insulator made of mineral wool for buildings. They are a leading company, globally a leading company on this. And in these two blue containers that you can see here, we deployed the pressure swing absorption and connected directly to the emissions of their cupola, where their product is being manufactured. And this is a photo of the PSA unit. The reason why I'm showing it is we are testing it as we speak for emissions at Rockwell, and at the same time, the unit is mobile and is available also to other potential interested users to apply pressure swing absorption to decarbonize their emissions. So the unit allows also to test advanced materials in these 4 small bypass beds with a few kilograms of materials. And I can show you some other pictures inside the container where it is installed with the mass spec to control all the compositions, a SCADA system for an automatic control of the system. Before I finish, I have to highlight that the project is still ongoing after RISE with IDRIC funding first, and currently with Impact Acceleration Account funding from the EPSRC. With this, I finish my presentation. I hope this was useful. We are working with Sustain. We are really focusing on the decarbonizing industry, and I'm keen to hear from you if you have any questions. Thank you.
Brilliant. Thank you very much, Enrico, for sharing information about your projects on Sustain UKCCSRC and the information about the pressure swing absorption unit as well. So now we've got our final presentation. So I'd like to introduce Professor Haroun Mahgerefteh from University College London and Paul Cobden from Swerin. Over to you, Haroun.
Hello, good afternoon, everyone, and thank you for the invitation. As just mentioned, this is going to be a double act. I do the simple part and I leave the difficult parts to my colleague, Paul Cobden, to cover. I thought it would be a good opportunity to give an example of a project which takes an integrated approach to the problem of capturing CO2 in the steel industry in the context of not just the technology development, but also all the associated aspects such as policy, business models, and also integration into an industrial cluster. So with that, I'd like to give you a brief introduction of our Horizon 2020 project that we started back in 2020. It's a 5-year project, and just give you a brief overview of what the project involves and some of our findings. So moving on, this is a snapshot of the project itself. It is primarily focused on the TRL-7 development of 2 novel capture technologies, which have provided considerable promise based on solid absorptions, namely the displace technology and cathode technology. So we work on the development of these 2 TRL-7, followed by integration into a steel plant, ArcelorMittal steel plant in Belgium. The other aspect of the project is that we are focused in line with the call itself in industrial clusters. So in the context of industrial clusters, when you integrate an emission source, there are also issues related to the transport, efficient and cost-effective and safe transport of the CO2, which is captured and ultimately destined for either utilization or storage. So that's another aspect of the project that we are focused on. And of course, being a technology which has impact, societal impact, so societal readiness is also an important aspect of our work. Finally, policy and business development models. CCUS costs money, basically. So we need to entice stakeholders to participate in these ventures. So having appropriate business models to entice stakeholder involvement, as well as policy instruments, are also important aspects of our work. In this project, we have we have 22 partners from a whole spectrum of different countries in Europe, including China and Canada and the USA, ranging from academics, business model developers, and policy developers, as well as industry. So main objectives are, as I mentioned, to elevate these 2 energy efficient CO2 solid-based capture technologies known as displace and cathode from TRL-5 to TRL-7 and designed for optimal integration in the steel industry. My colleague Paul Cobden and Swerin will explain a little bit more details in a minute about the details of these two technologies. Analyze the economic and environmental and business impacts and opportunities for integration of these two technologies at large scale, TRL line, as an example, in a steel production plant in Belgium, ArcelorMittal plant, which is part of an industrial cluster in the North Sea Standard cluster, followed by ultimate storage of the captured CO2 in the North Sea. Develop and test robust stakeholder and end users to assess societal readiness for CCS industrial clusters. And finally, as I mentioned, develop business models and policy instruments to facilitate stakeholder involvement. Now, the steel production industry, as far as the emissions are concerned, presents a unique, challenging technology as far as CO2 emissions are concerned. You have several places from which CO2 is emitted. Majority of it comes from blast furnace gas, which accounts for approximately 65%, followed by coke oven gas, sinter plant, and several other emission places. Now, what is unique is not just because the fact that the emissions come from different parts of the plant, but also the concentrations and the specifications of these CO2 streams are quite different. So it is quite challenging to develop a capture technology, which can handle these different types of CO2 with different concentrations and different types of impurities in one go. So our two capture technologies are basically designed to be capable to capture almost as much as 90% of these overall CO2 emissions from the different parts of the steel plant combined together. This is a snapshot of our various work packages in the project. I won't bore you with it. I just briefly went through it. So there are 8 work packages in total. The work packages 1 to 6 deal with the development of the technologies through to the long-term business models. And of course, as it is always a requirement, we pay particular attention to the dissemination and communication and public engagement of our project results. So I pass over to Paul Cobden from Swerin, who is going to talk about these two different capture technologies. Over to you, Paul.
Thank you, Haroun. So just very briefly, a word about me. I've been working in CO2 capture and hydrogen production for the last 30 years and 15 years with the steel industry, of which 5 years in the steel industry. As our very first speaker told you, there's really quite a lot of different sources of CO2 in steel making, as Haroun has also just highlighted. So in order to decarbonize the steel sector, we're going to have technologies that look at all of these different types of CO2 or that can handle them. And so in this first work package with the displace process, what we did was we looked at 2 very different manners of decarbonizing reheating ovens. Reheating ovens are very typical units of operation, both in traditional steel making and also in EAF steel making. So it's where you reheat the steel so you can form it and roll it and get the right kind of properties. So in the one case, we took blast furnace gas, which we oxyfied. That's the graphs at the photos at the bottom, and we removed CO2 from the exhaust of that gas. This is on the bottom. You see a 3 ton per hour walking beam furnace. Putting these 800 kilo steel samples through the furnace, 13 at a time, in order to assess if we can get to the right temperature with oxified blast furnace, and also if the properties of the steel remain unchanged, because that's a real important part for the steel industry. It's not the CO2, it's the steel. The steel that they're worried about, and that the properties are the same. At the top, what you see is an alternative way of decarbonising the reheating ovens, and that's to remove the CO2 and the CO from the blast furnace gas, which results in a nitrogen hydrogen product, and then to use that for reheating of the samples. So this was a world first, as far as I know, in terms of reheating using recovered hydrogen from a blast furnace to reheat steel. And so these are just two of the proxies that we have in terms of the whole case for decarbonising traditional steel making, but they have a lot of connections to secondary steel making and the EF steel making as well. Could we go to the next sheet, please? So in this project, we have actually two different types of technology that we're trying to demonstrate. Here you see on the right-hand side, this is called the displaced pilot. It's a 10-meter column, 60 centimeter diameter. It's filled with a material called hydrotalcite, which is an anionic clay operating at 400 degrees C. Normally, we'd use that in a PSA type of mode, but in previous projects, we found out that there was also a mechanism that occurred on this material called displacement. And so we could use that to create blocks of CO2 and steam that move through the column. And doing that, if we have a block of steam coming out of the column, that means it's really quite easy to reuse that steam in another column. And this reduces the overall parasitic loss of energy because of CO2 capture. So, I mean, all of these processes is about getting as an efficient process as possible. So recovery of steam at a relevant level is a really interesting thing to do. So I think it's almost a year ago now that we demonstrated the displaced technology at this type of TRL5 type of demonstration, TRL7 demonstration. Can we go to the next sheet, please, Haroun? So the second technology is called CASO. It uses two materials, one being calcium oxide, calcium carbonate, the other being copper. There's a three-step cycle for this process. You see the pilot plant built in Asturias, Spain, at the ArcelorMittal plant there. The special thing in this project is that if you need to decarbonize through calcium carbonate, you have to bring in a lot of heat into a process. And it just so happens that the reduction of copper oxide to copper using hydrogen is a very exothermic process. And this can produce heat right in the center of your reactor to decarbonize or to calcine calcium carbonate in order to make CO2 again. So with a rather simple cycle with three steps, we're able to decarbonize a blast furnace gas and also produce this nitrogen hydrogen mix for use in, for example, reheating ovens. So I'll go back to you, Haroun.
Thank you, Paul. So just to recap, in the context of the advantages of two capture technologies, one of the main advantages is the very low environmental impact. Packed bed reactors with virtually zero emission of particulate matter and zero emission solvent volatile compounds. The absorbents are quite stable, with very little attrition through repeated cycles. The above features are in contrast to conventional CO2 capture technology in steel plants that use post-combustion scrubbing with commercial and new generation solvents, which are prone to degradation and may have significant environmental impact. Moreover, another advantage is that our capture technologies produce valuable, as Paul mentioned, decarbonized products such as pure hydrogen that can be used to produce methanol, for example, or synthetic liquid fuels. In the context of key performance indicators, classifying the context in the terms of carbon captured, SPECA and CO2 avoidance costs compared to the two benchmark technologies, MEA and MDEA, we do considerably better. The percentage of carbon which is captured is expected to be up to 89%. SPECA 1.5 megajoules per kilogram of CO2, and the CO2 avoidance costs is 41 euros per ton, as compared to benchmark technologies, which can vary between 65 to 50 euros per ton. We are, of course, interested in the scale-up of these technologies through their integration into a steel plant. For package 3, focuses on the development of the process flow sheets for doing that, based on techno-economic assessment and to result in the specified performance indicators that I mentioned. For package 4, one of the main focuses of this work is also integration in industrial clusters. We all know that the most efficient way of decarbonizing CO2 emission industries is in the context of industrial clusters, where a common transportation network can be used to connect the different emission sources. With that, we chose the North Seaport Industrial Cluster as an example, where the ArcelorMittal plant is located, along with several other CO2 emission industries ranging from glass, polymers, fertilizers, which are distributed in close vicinity with one another, forming an excellent example of an industrial cluster where the CO2 is captured from these different emission sources via a main trunk pipeline followed by ultimate storage in the North Sea. So one of the important aspects of our work is the development of a multi-source dynamic flow model to enable the control of the flow of these different CO2 sources which are captured into a common pipeline network. It is quite a complex scenario, given the fact that these CO2 sources have variable flow rates, different CO2 concentrations. So when it comes to mixing them together and followed by ultimate storage into for North Sea, for example, you need to know exactly what is going on, how the concentrations are changing. You need to be able to control the quality of the CO2 and the flow rate and make it continuous rather than interruption. So developing a multi-source dynamic flow model where we can track these different factors such as CO2 concentrations and flow rates, and ultimately finding out what comes out at the other end at the storage site is one of the important aspects of our work. This is also combined with LCA to investigate environmental impact of the integrated C4U. So when it comes to LCA, of course, there are several factors involved. So you're using compressors, you use energy that also equivalent to CO2. If you are going to build pipelines, you produce steel. To produce steel, you emit CO2. So you need to look at the whole package when it comes to basically quantifying the effectiveness of your work. One of the important aspects of our work is also the safety aspects when it comes to transportation of CO2 in pipelines. You're dealing with huge amounts of CO2, which is transported. CO2 is, of course, an efficient at pressures at volume, 10% per volume. And if it is released, can give rise to can be extremely hazardous. We have, as part of this study, we have constructed the longest fully instrumented test pipeline in China, where we have conducted CO2 release tests in order to find out track the dispersion profile of the CO2, how the concentration of CO2 in the event of an accident changes with time as a function of different impurities, and develop workouts, safe work distances. There has been, of course, pipeline transportation is not going to be the main, the only transport mode. When we are looking at CCUS in the context of industrial clusters, we are also inevitably have to consider transport by ship, barges, trucks, and trains. So the development of a multimodal transport model for the CO2, where we come up with the optimum mode of transport involving these different transport modes in taking the CO2, capturing the CO2 from these different sources, and ultimately storing it or utilizing at a point. So one of the focuses of our work here is the development of this multimodal transport mode, where we take account of the costs, the environmental impact, and also safety implications by allocating different indices, weighting factors to each, and coming up with the optimal mode of transport. We have selected 4 sites in Europe where multimodal, with different industries, planning from Spain, where we look at the biomass power plant, in Italy, Iron Group waste to energy power plant, a steelmaking plant in Sweden, Alema, and also a cement plant in Germany, where they are all looking at the capture of the CO2 followed by storage. And we are applying our multimodal transport model in order to come up with the optimal mode of transport for each one of these different emitters, given the geographical locations and the topography around the plant. And finally, societal readiness and public policy are essential importance. Without industry societal readiness, societal support, CCUS won't go far. So you need to understand the needs of society in order to address their concerns, and also take on board the safety aspects to make sure that there is no environmental implications, and also safe operation. And finally, the development of long-term business models. CCUS is expensive, basically. It's not a money-making business, so we need to have business models where we can get involved based on different stakeholder involvements to facilitate investment. So with that, I finish, and I pass over to Kyra. Over to you. Thank you.
Thank you so much, Haroun. And thank you to all of our fantastic speakers today, Ed, Paul, and Enrico, as well as Haroun. We really appreciate all that you have to say. Such different and interesting perspectives across the decarbonization challenges of the steel industry.